Hello, welcome to lecture 20. So, the topic of course, the broad topic is explanation of corrosion event on the basis of mixed potential theory, and on lecture 18 and 19 we have talked about the effect of concentration polarization as well as activation polarization on the corrosion of an active metal. And we have taken the instance where active metal, the polarization is controlled by activation mode, whereas the cathodic reaction can have either activation control mode or concentration control mode. And at the same time we could also see how the experimental plot looks like in case of a situation where the corrosion is activation control. That means both activation polarization lines are cutting across, and in another case where the concentration controlled situation where, or rather concentration polarization controlled corrosion event, where the activation control part of that dissolving metal is cutting across the concentration polarization segment of the polarization plot of the cathodic reaction. Now, we will do a little bit of numerical problem solving, and we will start with one problem on concentration polarization effect, and then we will also start looking at another aspect that in practical situations we seldom use hydrogen electrode, rather standard hydrogen electrode is seldomly used. So, we generally use a much better stable reference electrode while we do experiment in the lab. We either use AgCl electrode, which are actually, and this is one reference electrode. Then we can use standard calomel electrode or copper sulfate electrode. We use copper sulfate electrode is more preferred in the industrial application point of view. For example, when we see the cathodic protection, in order to see the polarization effect of the electrodes, means either anode or cathode, when those cathodic couples are placed inside soil or seawater, that time we do see time to time the polarization potential of those electrodes. That time we mostly copper sulfate electrodes are used. So, because those electrodes are much stable electrodes, that means every time it will give the same reference potential, but in case of hydrogen electrode, maintenance of the stable potential is bit tricky, and that is what the potential many a times we measure with reference to those standard hydrogen electrodes which are not standard hydrogen electrodes. So, that potential part will be little different. Till now whatever calculations we have done on the basis of standard hydrogen electrode. Now, we will do see the effect of calomel electrode. We will take calomel electrode this time and see how to calculate the polarization, how to solve a problem when something is corroding, and there also we will make use of mixed potential theory. So, the first problem, let us take up the problem 1, and the statement is like this: we have to calculate concentration polarization, we have to calculate and the situation where silver is depositing. See the cathodic reactions, and in this case we are considering cathodic polarization, for the understanding of concentration polarization part. So, now cathodic polarization, cathodic reactions could be several types. For example, one type could be oxygen reduction, which is 2H2O plus 4E equal to 4OH minus. There could be reaction like O2 plus 4H plus 4E equal to 2H2O. So, these are two cathodic reactions. There could be reactions like this, there could be reaction like +2, this is also reduction reaction or cathodic reactions. There could be reduction like Ag plus E equal to Ag. So, the Ag, since Ag is very strong, Ag plus is a very strong oxidizer. So, that means it has always a tendency to get reduced. So, this reduction reaction can happen. Now, here Ag is silver is depositing, that means we are considering this reaction. Now, depositing at a rate of, if I try to find out the rate, so the rate of deposition, it is 5 into 10 to the power minus 1 gram per meter square per minute. So, this is the deposition rate, and in that situation IL equal to 400 ampere per meter square. So, that means this is the maximum deposition when this reaction, if I try to see its polarization effect. So, let us say this is my E equilibrium Ag at the concentration what we have in that particular Ag solution. So, it will have its plot like this. So, this is the plot we are getting. So, this is log I, this is E voltage, and here we are considering standard hydrogen electrode, reference electrode. So, this particular indication is IL, which is nothing but 400 ampere per meter square. Now, we have to find out the concentration polarization. So, this value at the rate of deposition, which is corresponding to some current IC at IC Ag. So, because this deposition rate can be taken in the form of cathodic current density. So, in order to attack that, we have to find out this value. So, how to find out that value? So, we can find this value as we know this equation. NF, this equation you know, and what are those values? This W equal to weight in gram, A area in meter square in this particular instance, T I can take it as time, let us take it as second, because we will come to see the why we are taking second, because we have to convert this particular thing into in the form of ampere, and 1 ampere is nothing but coulomb per second. So, that is what we are, this is this A and this A, these are similar. So, let me put it as amp. So, I is current density, F 1 Faraday, 96500 coulomb, N is number of electrons. In case of Ag, this value is 1, because we are considering this reaction. So, if we see this particular quantity, it is basically 5 into 10 to the power minus 1 gram per meter square per minute. So, I have to convert in this particular thing into gram per meter square per second. So, 5 into 10 to the power minus 1 divided by 60, it becomes gram per meter square per second. So, I can find out this IC corresponding to IC Ag because this is nothing but IC Ag, which is cathodic current density corresponding to the deposition rate of silver. So, 5 into 10 to the power minus 1 by 60 equal to I, and now A here we missed one point. A is nothing but atomic weight of silver. This is in also gram, and A of silver equal to 107.87. So, into 107.87 divided by 1 into 96500. So, I would get I to be 7.45 ampere per meter square. Now, once we get this, then I can find out concentration polarization value, which is 0.059 n log 1 minus IC by IL. Now, remember that calculation what here we are doing, all the calculation we will be doing at 25 degree Celsius as well as 1 atmosphere pressure. Fine. So, this is the condition. So, that condition only this value will become 0.059. So, I can calculate this value like this, 0.059 by n log 1 minus 7.45 400. So, this becomes minus 0.48 millivolt. So, we could see that the potential drop, sorry, here we have to put a minus sign. So, here we are putting minus sign, this becomes plus, but actually since we are considering concentration polarization, so this will be going downwards. So, other way around I can remove this part just to take that minus sign. So, here I can put a minus, fine, because its concentration polarization for the cathodic reaction will always go downwards, because we are considering cathodic polarization. Now, this is the value we are getting. Now, if I try to, let us say this, that means we have a very so, if we try to see the current value. So, if the current, this is the current value we are considering 7.45 ampere per meter square. So, at this condition the polarization, and this is the equilibrium silver potential, equilibrium potential. So, the drop would be from this E equilibrium Ag very minuscule, which is 0.48 millivolt. Now, if we just for sake of taking an example, that what will be the effect of the current on the polarization, concentration polarization. Of course, there if we try to find out the activation polarization, I could see the activation polarization, this is equal to neta concentration, but activation polarization is substantial, okay, because here it is going along this line, but concentration polarization effect would be very minuscule because of this very equation. This very equation we have to see. Okay, so, this is one sort of problem, but you just try to put this current value, different value, and keep going towards close to this IL, which is 400 ampere per meter square. You will see that the influence of that increase in current here, until unless it reaches close to that 400 ampere per meter square, it will be very small change because of this again I am telling this because of this very equation. Now, this is one problem on this cathodic polarization part. Now, in the next lecture onwards we will be taking up passivation, and then mixed potential theory will consider for explaining corrosion rate of passive metals. Before we get to that, let us, as we have mentioned in the beginning of this lecture, that we have to consider influence of a measurement by different other reference electrodes. So, let us solve some problems. One problem, this is let us say problem 2. Problem 2. So, the situation what we are considering, if we measure potential by some other reference electrodes other than of course standard hydrogen electrode, and here we are considering standard calomel electrodes. This SCE means standard calomel electrode, and the potential, the equilibrium potential for SCE we take up 0.241 volt, and this is measured with reference to standard hydrogen electrode. Okay. So, if we measure any potential with reference to this electrode, so what will be the situation? So, one problem could be constituted like this. Let us say a platinum electrode is considered. So, if we take a platinum electrode and if we consider that platinum electrode is in a solution, and this is in a solution or the electrolyte is having pH of 12. So, this is the pH, solution pH is 12, and this is and in that situation we are seeing oxygen evolution on platinum electrode. So, these are the three statements. These are the three statements. Now, since it is pH 12 and since it is oxygen evolution, immediately we could make out that the reaction what we have to consider is for OH minus equal to O2 plus H2O plus 4E. So, this is the reaction we should consider. Now, we could see that oxygen evolution can take place if the reaction is anodic. That means the reaction is moving this way. So, that means anodic reaction we are considering. And if the potential, let us say we are using the standard calomel electrode, that time the potential over platinum is measured to be 1.5 volt. So, this is the voltage what we have measured with reference to standard calomel electrode. So, this is the way it is expressed. If you are measuring potential with reference to hydrogen electrode, it is always better to mention SHE volt, and in case of standard calomel electrode, so we are writing SCE. Now, if we see this, that means this is the volt what we have measured on platinum. So, remember here platinum is not dissolving. So, the platinum is acting as an electrode on top of which oxygen evolution is taking place. So, we are taking the reaction this reaction, and here since it is anodic reactions, we are considering anodic polarization. Now, if we take anodic polarization and if the potential is this, now our problem, which the part what is to be determined is we have to find out over voltage is how much is the over voltage. So, over voltage, since it is anodic, so of course we have to find out neta A, and this is to be found out with reference to standard calomel electrode. So, this how to solve this. So, let us plot this. In order to solve this, we have to see what could be the correlation of this polarization with reference to Pobe diagram. So, if we see the Pobe diagram for water, so this is E voltage, and that is always plotted with reference to standard hydrogen electrode, and this is pH. So, we could see that hydrogen lines are two parallel lines, this water lines are two parallel lines, where H2 is stable between these two lines, and this is the line which is hydrogen line, this is oxygen line. And if we see the pH 7, below pH 7, the reaction which is governing is 4 plus 4E equal to 2H2O, and then on the right side it is O2 plus 2H2O plus 4E equal to 4OH minus, and this side is H plus E 2 equal to H2, and in this side the reaction that happens is water reduction, H2 plus 2 OH minus. So, this is the reaction that happens when the pH is more than 7 or equal to 7, this reaction takes place. And now, in this zone we have stable water, and this particular potential is 1.227 volt when pH is equal to 0, and this voltage is 0 volt when pH is equal to 0. Now, since we have taken pH to be 12, so this is 12 pH. Now, when we are taking 12 pH and we are considering oxygen evolution, that means of course we are looking at this particular line, and since its oxygen evolution is taking place, beyond this line oxygen evolves and below this line hydrogen evolves. So, the beyond this oxygen is evolving. So, we have to first consider the equilibrium potential at that pH. So, this is going to be my E equilibrium O2 reaction. So, E equilibrium O2 would be, we know the equation governing this particular line, which is nothing but 1.227 minus 0.059 pH. So, this is the equation that will tell me the point here. So, this is volt, and remember this is with reference to standard hydrogen electrode. And now, once we determine that, so this becomes minus plus 0.19 volt. So, we know what is the equilibrium. Now, let us draw E versus log I plot. So, since we have considered standard calomel electrode, this potential. First let us draw those potential axes. Now standard calomel electrode has got a potential. This becomes 0.241 volt. This is with reference to hydrogen electrode, and then hydrogen electrode has got a potential. Let us say this side is hydrogen, this is standard calomel electrode, and this is hydrogen electrode. So this potential is 0 volt. So with reference to standard hydrogen electrode, so this is 0 volt, and here this is 0.241 volt. So now we are seeing this with reference to standard hydrogen electrode, this potential is 0.519. So with reference to standard calomel electrode, this value becomes, because when standard calomel electrode we are using, this is my reference potential, so that becomes 0. So 0.519 minus 0.241 equal to 278 volt, 0.278 volt, and we have gone up to 1.1 volt. So with standard calomel electrode, this is 1.5 volt. Okay. So now if this is 1.5 volt, and now this value we have considered, this is the potential what we have considered with reference to standard hydrogen electrode. So this potential would become 1.5 plus 0.241 equal to 1.741. So that means this potential is way beyond this potential. So of course oxygen evolution would take place. So now we have to find out the polarization with reference to standard calomel electrode. So the standard calomel electrode, the over voltage would be, this would be the measurement of standard this over voltage. So this Na becomes, neta A becomes 1.5 minus 0.278 equal to 1.222 volt. So this is going to be the over voltage what I would experience. So this becomes, because why? Because this point corresponding to standard calomel electrode, I will see the voltage to be 78 volt. So this becomes my neta E, and this is the value what we are going to see. So let's stop here. We'll continue our discussion and try to see some other problems in our next lecture. Thanks a lot.